Hello, this is the separating techniques, practical. I think I'm going to try and do about 4 demonstrations. Let's see how long it takes. The first one, very simple one, this is a separating funnel. It's the shape of a funnel, it's got a tap, it's got a stopper on the top, and I'm going to put some water in there. It's water from the tap water. Can you see? I can see the liquid. And then I'm going to mix with that some oil. Now, oil and water don't mix. The chemistry word we use is they are immiscible. Immiscible. I try and remember it by thinking about not mixable. Immiscible. Not mixable. Right, so if I pour some of the oil in, this is Sainsbury's sunflower cooking oil. So put the oil in. I'm hoping you can see there. You get 2 layers. The bottom layer is the water and the top layer is the oil. So, common sense, if I put that in there to separate the two, I mean, sometimes if you have a mixture, it might be mixed up. Look, mixing it all up. Don't want to shake it too much, otherwise we'll have to wait longer for it to separate. But then, once it's mixed, if you just let it settle, you just let the 2 layers settle by not moving it around, then you can use the apparatus to separate 2 liquids that are immiscible. So the way we're going to do this is open the tap, and you're going to look for the partition, the division between the 2 layers, and we're going to stop it before the oil gets into the beaker. So beaker, clean beaker, collecting water, the division is getting closer, and before the tap I stop it. Right, so that is tap water. Now, I'm going to use like a waste beaker just to take us into the oil region. So the last few drops of water are coming out. Now the oil's coming out. I'm going to let it run until I'm sure the oil's coming out there. That's the waste beaker. That's kind of got the boundary between the 2 in. And then I can get another beaker and I can open this, and now what I'm collecting is the Sainsbury's sunflower oil. So, very logical method, relies upon densities of liquids being different. The lower density liquids float on top of the higher density liquids when we have immiscible mixtures. And that is one demonstration. Now the other 2, simple distillation. And just swap the camera around if I can. Right, here. Maybe I need to just move the camera a bit. Right, so this apparatus, I set it up a few minutes ago. I've got here, this is what we call a mantle, and I'm heating up a mixture of ink and water mixture. So the mantle heats up this mixture, and this mixture here is a solution. So the solvent there is water. The water is dissolving the ink. The ink is the solute. Now the ink solute is a dark solid that's dissolved within the water. And simple distillation involves boiling this. You want to boil this. As it boils, the vapors will rise up, and in this case, the solvent being water, the vapors will be steam. as the steam rises up, it's going to show on this thermometer what temperature we have. And I don't know, can we see the thermometer temperature? At the moment, the thermometer temperature is about 20 something, I think. If I can focus it, yeah, 21-ish. And therefore, the steam hasn't started coming through yet. But when it does, it will hit the T-junction there. Then the steam will be forced to come down here. And this is the clever bit. This is the Libre Condenser that I talked about in my theory of separating techniques video. And that's got two layers. So the outer tube, I'm passing water through. Can you see this bottom, the bottom tube, this one? Follow that along to the tap. The tap is on, and the water goes from the tap through the condenser and down out of this tube. And can you see? There is the water that's running through. That water running through the condenser on the outer tube will cool that condenser down. Now if I touch it, that's really quite cold. Typically tap water is about 16 degrees, and that feels cold to me because the room is about 25 degrees, and 16 degrees is going to feel colder as a consequence. And when this eventually, the temperature of the mixture is getting more and more and more as we wait for the mantle to heat it up. The mantle, see, it's on, it's heating it up. You can see some droplets of evaporation is increasing, and when that boils, I'll show you again, but when it's boiling, the steam will be coming down here. As it does so, when the steam comes down here, it will be cooled by the cold water, and the inner tube will be where the steam will be, and the inner tube will be cooled by the water that's in the outer tube, and the inner tube steam will condense back into droplets of water. By the time it hits this adapter, by the time we get to the adapter bit at the end here, then we're hoping drops of water are going to come out the end, and we're going to collect the water in this fresh beaker, empty beaker. Going to collect the water from the adapter, and that's the whole arrangement. Right, while we wait for that to cook, I have set up, in the same way, I've set up fractional distillation as well. Now, can you see the difference? The difference, if we start from this end, adapter, Libre Condenser, thermometer, T-junction, that's different. Look, that thing there, I'm going to hold that thing, is the fractionating column. And that fractionating column is what is different. And that fractionating column makes this apparatus fractional distillation. I can't get it all in, let me just step back. There. So that's the fractional distillation apparatus. That is the simple distillation apparatus. The word simple distillation just involves boiling the mixture, the solvent boils over as a vapor, the vapor is cooled and collected. Fractional distillation is similar, except it has an extra fractionating column, and we use fractional distillation with a mixture of liquids that may have similar boiling points. Alcohol and water is the famous example. And here, when that mixture starts to boil, it's not boiling yet, we'll have a look, not boiling yet, it is getting hotter as we speak, but when it starts to boil, the mixture will go up, and the lower boiling point, that's the alcohol, the lower boiling point liquid will boil first, and unfortunately carry with it droplets of the other liquids present. So in this case, we'll get alcohol vapor going up. As the alcohol vapor goes up, it's going to carry with it some droplets of water that we don't want, and this fractionating column hopefully will reach the temperature of the alcohol vapor, which is 78 degrees. The temperature won't go above 78 degrees because the alcohol vapor being 78 degrees will keep it at 78 degrees. And at 78 degrees, water will be given a chance to form droplets on this, the little pieces of glass on the inside of most of these fractionating columns. This is a posh fractionating column. We bought it as a fractionating column, so when it was made, they pushed through a kind of needle and they get glass of the wall. The wall glass has been pushed in rather than little beads of glass that I've used in previous schools. So in these beads or in the glass, the water is given a chance. Water is given a chance to form droplets on the beads and drip back down into the flask, whereas the alcohol will keep going up, and then the alcohol vapor will get cooled down by the condenser in exactly the same way as I talked about earlier. It'll get cooled and it'll form pretty pure, like 99% pure alcohol will come out the end, and we'll collect it in that test tube there. Okay, so all three demos are underway. We've done the first one. Let's come back to the distillation, the simple distillation there. Look, that simple distillation now is boiling. Boiling, right? I wonder if we see the temperature. Temperature on the thermometer is rising. You see that? It's 95 degrees or so. 95 degrees or so. These thermometers with the blue fill thermometers are not great in terms of accuracy. So when it says 95, I wouldn't trust it. Give or take 10 degrees. I think that may well be 100, but it's showing 95. Rubbish thermometers compared to the mercury thermometers we used to have. And so let's have a look. If the steam is rising up, showing 100 degrees on the thermometer, if it was a good thermometer, then the steam will hit that T-junction there. You can see it hitting the T-junction. As it hits the T-junction, it's then going to go down this condenser. I hope you can see the condenser, the droplets of steam. That is hot. That is hot. But that is not hot, that's cold. So that's cold, but anything further up is hot. Steam's coming down there, making that 100 degrees hot. And when it hits here, the cold water is cooling it down. You can see the droplets of steam. The drops of steam are now making droplets of water. As further down you go, by the time you get to here, it's drops of water. And the drops of water will start to come out the end soon. There we go. I can see a droplet of water coming. There it is. It's coming out the end. And that is simple distillation. See it bubbling away there? That's the water boiling off at 100 degrees. The ink solute stays behind because it's a dark solid. There's no darkness coming through here because the dark solid stays in the mixture there. And that's pure water coming out the end there. Pure water, not a hint of darkness, because the solute stays in the flask. Now you might ask why we're using electric mantles. Well, in this practical it doesn't matter. In this one, there's water and ink which cannot set alight. So we could use a Bunsen burner. It's just convenient to use a mantle because we've got them. But on this side, it would be dangerous to use because a Bunsen burner might set the alcohol alight. And we don't want that. So where there's a chance of, if we've got a leaky apparatus, and alcohol vapor comes out of here where my thumb is, where my finger is. If it comes out of here and you had a Bunsen burner, you could potentially get a fire, and we do. When boys do this with a Bunsen burner, they do get fires. and we haven't got enough mantles for all the boys to do that. So we do use Bunsen burners and we do have fires. We just got to be careful that we warn the boys and get them to deal with the fires and just be sensible with it. So here, look, fractional distillation now. This is the hardest thing to understand. So I'm going to run through it. Can you see that? That is a mixture of alcohol and water. Alcohol-water mixture boiling. As it boils, can you see? The vapors go up. Vapors are going up. The thermometer reads at the moment. I can focus it. Come on. The thermometer reads at the moment, it's about, well, it was about 30 degrees. It's shooting up. It's shooting up because the alcohol vapors are reaching that thermometer bulb. Look at that thermometer bulb. Is it looking a bit wet? A drop there. That's probably a drop of water going back down. So can you see, as the mixture boils, the alcohol gas is going up. As it does so, it gives a chance for the water that may be present to drip back down. So those drops there dripping back down, those drops are drops of water dripping back down into the water alcohol mixture. So the water is given a chance to drip back down. That's the importance of this fractionating column. And then what we have is any alcohol that reaches the top, will hit the T-junction. See that? 73 degrees. Again, don't trust the thermometers, but that's probably 78 degrees in reality if we had a good thermometer. So at that T-junction, the vapors, the alcohol vapors, at that T-junction will be forced to go down here. As they go down there, that's the condenser. The condenser is, same thing here, that section is cold. That section is, that's hot. Not as hot as the water. One that was 100 degrees, this is about 78 degrees. So this cold section condenses the alcohol vapor back into drops of alcohol, and the drops of alcohol will then, at the end, go down that adapter and drip into that test tube that we've got, collecting almost pure, like 99% pure alcohol from the mixture, which was like 50% pure alcohol. 50% pure, it goes up. As it goes up, the alcohol vapors carry with it water as impurity. The further up we go, the purer alcohol percentage we get. Towards the top end, we've got about 99% pure alcohol. The water has dripped back down, and the alcohol vapor at the top is forced to go down the condenser. The condenser cools the alcohol vapor back into alcohol droplets, which are collected. And unfortunately, you do get a little bit of water making its way all the way up with the alcohol gas over and across and down. And so we do get a little bit of contamination. If we wanted better separation, we would have an even taller fractionating column. Yeah, see the thermometer there still reads 74 degrees. And that is just a function of the poor, cheap blue-fill thermometers. The mercury thermometers we used to use were so much better. So that's fractional distillation. I hope you understand how it works. Fractional distillation is used for liquids of similar boiling points. That's simple distillation. Simple distillation just involves where you want the solvent that's present in a solution. That is your separating funnel that is used to separate immiscible liquids. And I'm going to stop the video there, and maybe I'll set up chromatography as the final chromatography apparatus is there. Just, it will take me a little while to set it up. I'm going to stop the video and I'll come back to you. So welcome back. I said that there was just chromatography left, but it occurred to me I've not talked about crystallization. So do you remember having the ink and the water, and the water is a solvent, the ink is a solute, and we use simple distillation to separate the water from the solute, which is a dark solid. Well, what if you want the dark solid? What if you want the solute and you don't want the solvent? Well, then the technique to use is crystallization. So you get a crystallizing dish, or otherwise known as evaporating basin, evap basin, etc. And I'm putting the solution into an evap basin. My input's fallen out. And I'm going to start heating it. Now, perhaps you can see it better from a distance. I'm going to get roaring flame underneath. And the idea here, the idea is that we're going to warm up the solution. The particles start moving faster and faster and faster and faster. The evaporation rate will increase, and eventually it will boil. And when it boils, it's the water at 100 degrees-ish that will leave. The water will leave a steam, and the dark crystals of ink that we use will be left behind in the evaporating basin. Now, rarely in exams are you asked, well, never are you asked about separating ink from inky water. More commonly, you're asked about copper sulfate. So copper sulfate is water with copper sulfate as a chemical inside, and how would you separate the copper sulfate from the water? And you do the same thing, crystallization. So I've got a second experiment here. I'm going to run them both together. I'm going to run them both together and keep an eye on both of them. So one of them, I've got the inky water, and the other one, I've got copper sulfate solution. And it'll take a little bit of time for them to start boiling and for crystallization to happen, and I'll come back to it. In the meantime, I can show you chromatography. Now, chromatography. In the old days, we would have done chromatography a bit like this. We would have got a filter paper, we would have got some kind of dark pen, we would have put a blob in the middle like that, and that's black felt tip, that black felt tip there. So black felt tip ink is made from a few different chemicals mixed up together, and how we might separate them would be that we would have to drop. I don't, 1 minute, I'll have to get a dropper. Right, I've got a dropper. I'm going to put some water. And we would drop drops of water onto our blob. Carefully, 1 drop. We'll let the drop spread out. You have to have a lot of patience for this, otherwise you just end up with a wet puddle in the center of the paper. That's after 1 drop, it's spreading out. As the water moves outwards by capillary action, then it carries the chemicals with it, and you get like lines, or circular lines, representing the different chemicals that are in the ink. Can you see? The blue is moving with the water faster than the darker purple that is moving with the water slower. And again, another drop. And it takes time and skill, and there is a better way to do all of that that requires much less time and skill. So, beaker, I'm going to put some water in the beaker, not much. I'm going to get a pencil and I'm going to draw a pencil line, and then I'm going to blob the black ink onto my pencil line, maybe brown ink, black ink, brown ink, maybe red ink, and those three, like that, blobs, I can try and separate. The key thing is, I don't want the water to reach the blobs. So I'm going to tip some water away. That seems to be a bit close. I want the water to move upwards, watch. So, a little bit of water, put that in there. Maybe show you the other way around. That way around. I'm going to just put that down. Actually, you can see, I think I can see on my phone, that the water, by capillary action, is indeed moving upwards. Now, as the water moves up across the stationary filter paper, then the chemicals that are in the blobs will move with the water, upwards with the water. Now, the faster chemicals will rise up more than the slower chemicals traveling with the water. So in a sense, we look at the waterfront and we can see, with that black ink for example, we can see that the blue colour is toward the top end, the purple colour is being left behind. So there's probably one chemical that's blue that's used in that black ink. There's another chemical, purple, which is a little bit slower travelling through water. And then the brown ink and the red ink. I think with the red ink there's just one chemical, red. I really can't see the brown very much at the moment. But the key thing here is that you must stop. You must stop doing the chromatography experiment. You must stop it before the water reaches the very top, because from the very top it's got nowhere to go. When it reaches the very top, if you were to keep the chromatography experiment going, then it would, at the very top, all of the chemicals would catch up at the very top, and we'd all end up with things at the very top. And watch, take it out when it's near the top. Now that's called a chromatogram. So what you get when you do chromatography is a chromatogram. Can you see the separation? And that separation is a function of different speeds that it will travel with the water as the water is traveling. In any normal chromatography, there's always something moving. In this case, it's water. And it moves across an obstacle like filter paper, which is the stationary phase. Stationary phase is filter paper, mobile phase is the water, and the chemicals in the blobs travel at different speeds and separate. Now, that dropwise thing, can you see how it's similar to my blob, except the separation is all the way around? The blue chemical is indeed moving faster with the water than the purple chemical, which this shows as well. The blue is at the top end, the purple is following behind, and here you've got the blue on the outside, the purple following behind, and that does a similar thing to this. both of them are called what they're called paper chromatography. So paper chromatography, they're all paper chromatography, and that is one of the techniques you need for GCSE. So, can we get back to this then? So back to crystallization to finish off. The crystallization, can you see? This is boiling. Maybe if I bring you closer, can you see? Let me just if I bring you closer like that, you can see the steam coming off, perhaps on this angle you'll see it in the background of the dark bench better. You can see the steam coming off, so that means water is being driven off. As water's driven off, there's no dark solid being driven off, just the water being driven off. So eventually you'll be left with crystals of ink here, and on this side you'll be left with crystals of copper sulfate. And if you watch my video where I explain this, if you want good crystals, like you want crystals to be bigger, then you would you'd turn the Bunsen burner off and you would leave it. Now if you leave that for days, then you'll get some nice big fat crystals. Whereas if you boiled away the water today, you get teeny weeny tiny crystals. Well, same thing would happen here. This is just a different solution, inky water, as opposed to copper sulfate and water, ink and water, copper sulfate and water, and this process gives you the dissolved things, and the dissolved things are the solute, and we are left with crystals of the dissolved things, and that's why the process here, that technique is called crystallization. Right, okay, I'm going to stop there, and I hope you understood that separating techniques video.